When the idea of building the James Webb Space Telescope was proposed for the first time in 1969, the first exoplanet had not even been discovered. At that time, the fundamental goal of Webb was to study deep space galaxies in infrared wavelengths, and the word exoplanet was not even in Webb's dictionary. But as the first confirmed exoplanet detection was made in 1992, Webb was customized to study the extrasolar planets as one of its primary science goals. And today, it is one of the best space telescopes launched to study the atmospheres of exoplanets and search for the building blocks of extraterrestrial life. Only in its first few months of being operational, Webb has begun a revolution for the exoplanet researchers. From revealing the transmission spectrum of an extremely hot gas giant to discovering a super-Earth that possibly harbors a global liquid ocean, the James Webb Space Telescope has already shown its potential. But the question is, are we ready to study what the most advanced space telescope will reveal about exoplanets? Unfortunately, the answer to this question is not much on the positive side, because as per a new study, there is a high risk that astronomers might misinterpret signals from Webb if the current models are not improved. So what's really the problem here? How do astronomers risk misinterpreting the James Webb data? Finally, and most importantly, how can we improve our models to make the best use of Webb's observations? Before we talk about the problems with our models, there's an important concept that you must know. Photons of different wavelengths interact with material in different ways. Some of them can pass through a material, while others get absorbed, and some even get reflected. The interaction depends on several factors, including the material's temperature and pressure. This concept is valid in the case of exoplanets too. When an exoplanet transits its star, as seen from the Earth, the starlight passes through its atmosphere and gets modified. That's because the different wavelengths of starlight interact differently with the atmosphere of the exoplanet. Astronomers can then compare this filtered starlight with the natural light of the star to know the composition of the exoplanet's atmosphere. They use the telescope's light-parsing precision to decode the atmospheres of some of these nearby worlds. And then, to interpret the data obtained from the telescope, they use opacity models. An opacity model clubs everything together and studies the spectrum of light after it interacts with the planetary atmosphere. These models can decode the type and abundance of chemicals in that planet's atmosphere. So far, the decoding instruments on board different telescopes, including the Hubble Space Telescope, have been doing a decent job. But researchers believe that with Webb's next level of precision, our current decoding and translation process will prevent us from catching important subtle details. And sometimes, this information might be as important as making the difference between a planet being habitable or not. Usually, 1D models are employed to extract information from the available data. However, research says that these models are insufficient to capture the changes in spectral lines arising from the asymmetries in the day-night temperature on a planet. Also, they do not compute the interference of clouds and haze in a planet's atmosphere in the spectrum. Sometimes, even the inhomogeneities present in the host star can either mute or enhance a planetary system. For example, sometimes spectral lines get distorted due to collisions between molecules, leading to pressure broadening, and the atmospheric studies within our solar system have been compromised several times due to unavailable pressure broadening parameters. In the present study, astronomers put the most commonly used opacity model to test to understand the impact of imperfections in opacity models. They did sensitivity analysis with 9 different opacity models. They tweaked the model a bit to include some limitations in our understanding of light-matter interaction and saw what atmospheric properties a model would derive. They found that each perturbed model led to different ranges of predictions for the properties of a planet's atmosphere. For example, in this figure from the research paper, you can see different atmospheric parameters like temperature and the density of different molecules of a super-Earth induced by perturbations in the 9 opacity models. Different colors represent cross-section corresponding to various models, while black dotted lines represent the actual values in generating this spectrum. One can see deviations up to a significance of 20 sigma, which is visibly large. It was concluded that if existing opacity models are applied to light spectra taken by the Webb telescope, they won't be sensitive enough to tell whether a planet has an atmospheric temperature of 300 Kelvin or 600 Kelvin, or whether a specific gas takes up 5% or 25% of an atmospheric layer. And sadly, uncertainty at this level can pose major complications in constraining planetary formation mechanisms and identifying biosignatures. Along with this, the team found that every model also produced a good fit with the data. This means that even though a tweaked model produced a chemical composition that was known to be incorrect, it also generated a light spectrum from that chemical composition that was close enough to fit with the original spectrum, as can be seen in this figure, where blue color shows the best fit model. This hints that the situation is more complicated than we thought it to be, because there lie enough parameters that can be tweaked, and even with a wrong model, you can still get a good fit and vice versa. This simply means that you wouldn't even know that your model is wrong and what it's telling you is wrong. So, is there any way to overcome these challenges? Well, there seem to be some possibilities. First, we need to include more laboratory measurements and theoretical calculations to refine our understanding of how light and various molecules interact. We know the Earth's conditions well enough, but as soon as we move to different types of atmospheres, things change, and we are at a high risk of misinterpreting. Hopefully, we'll be able to figure things out. If not, we will never be sure if what we observe with Webb is true. Just months into observations, the James Webb Space Telescope has already challenged our current cosmological models. We have covered everything in detail in this video. This concludes the 29th episode of the Sunday Discovery series. So if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos of this series.